381. Anyone have problem with 381? So we're very comfortable with flow accelerating, creating a vacuum at the float where the velocity is the highest and the pressure is the lowest, always. Questions on this one? Yes?
Was the pressure in the beginning, did it end up being atmospheric pressure?
Yeah, that's a very trick question. The last part is so counterintuitive. What is the pressure here? You assume an illicit, no friction fluid. That's what you assume. All right, so you apply Bernoulli from 1 all the way to the exit. Same area, same velocity, no gravity. What does it take to push the flow through? What pressure it takes to push the flow through? Nothing. Does it happen in real life? No. Why not? We have friction. You have friction. You give me a straw, even without this net, blow air through, I have to have a higher pressure from my mouth to push it through. It's never illicit. It's never frictionless. There's always a pressure. But if you assume it's frictionless, you get what you ask. It doesn't take any pressure to push the flow through. Okay? So it's a trick question, but it's really good to get you thinking about why is it not physical. Yes?
I'm a little bit confused on that because, so he did a Bernoulli from point 1 to 2.
Uh-huh.
2 is the point in the throat.
Yes?
What did you, like, why is the pressure not also negative at 1?
The pressure, based on what we assume that the flow is illicit, from 1 to the exit, let's call it the exit. This being ambient as a free jet, right? The pressure going back to 1 must also be atmospheric from Bernoulli. And it's counterintuitive simply because you assume the flow has no friction, right? And to do the first part, you don't even need this at all. You go from the flow to the exit. And always, anytime you see a shape like this, what's this called? 21, some of you in 2124, a shape that goes neck down and open up again. It's a venturi. This is a venturi. It's kind of like how you work in your carburetor. And all it does is to accelerate the flow and create a vacuum. That's all it does. Right? That's from Bernoulli. So, building on that, the next homework, 39, problem 30. Sorry, chapter 3 of problem 90 is I have a tank which is open, meaning it's atmospheric, and at a certain height, that's the gravity-fed problem. It goes through a pipe circular, as a symmetric. It has a flow, just like what we did for this problem 81, right? So gravity fed the flow. Which point along this flow path it has the minimum pressure? Or let me rephrase it. Which point along this flow path has the maximum velocity? At the flow. How do you know? How do you know? From continuity, thank you. Not momentum, not Bernoulli. Strictly continuity, right? Do you get it? Which point along this flow path has the minimum pressure? At the flow, why? From continuity? No. From momentum? No. From what? From Bernoulli. Okay? If I keep increasing the velocity here, this is water, and the pressure keeps dropping. and keep dropping, and keep dropping, and keep dropping. What happened to the water? How do you boil water without adding temperature? To change the pressure. If I have a pressure cooker, keep putting a suction, eventually without any heat, the water will boil. Anyone been to Denver? I just came back from Denver. It's a mile-high city, right? Why is it called mile-high city? It's a mile above sea level. Have you tried cooking at a mile above sea level? It's very difficult. It's all different because the pressure is different. So the problem is that at what point will the water boil? Water boiling is called cavitation, which bubble will form. Okay? So you're given the vapor pressure for water as a problem statement, very low, like 1.6 psi absolute. So if you at sea level want to boil water, keep pulling a suction until you reach 1.6 psi pressure absolute, the water will start boiling. So with that given, can you figure out the rest of the problem? And that's what I need you to work on. All right? So the rest is up to you. Maybe just a touch more hint in that you will have to find out from the problem statement. I won't dive into that. You have two equations. You have two unknowns. The velocity in the flow path, and also the h is the height at which this cavitation will occur. So you need to figure out where and how many times you have to apply Bernoulli to make this problem workable. So the remaining 15 minutes, give you 5 minutes for the quiz or more. Let me set you up for this special problem because it's certainly not trivial. And it really boils down to when to use Bernoulli and when not. All right, that's the spirit of what this problem is all about, SP1. So I have a large reservoir to the left, feeding a flow into a long channel, which different things happen. Yes?
Going back to these problems, will the solutions be posted even though homework's not being collected?
Yes, we have been doing that.
Awesome.
I think you need to check that, and if we're not, please let us know. Yeah, every time without collecting homework, it will be posted. And if I were you, I'll stay on top of it. Please don't wait until test 2, and then you go look at all the solutions for the past 4 weeks. It's too late, right? If you don't find anything on Canvas, please let us know. So what we have is different station. Along this flow path, and we'll call station 0, which is far, far upstream, in this big tank where the area is presumably infinite. And the remaining station 1 to 4, different processes happen in this two-dimensional rectangular channel. 1 to 2, I'm introducing a fluid perpendicular normal to my flow path, and you were told that this creates some mixing in the station between 1 and 2, so the flow is turbulent. From 2 to 3, I have some type of heating, relatively mild, temperature-wise, to the extent that the density can assume to be constant, not enough temperature to change the density. So, constant density flow. Stations 3 to 4, I am withdrawing the liquid from my flow path. Also normal to the wall. So in the diagram or the statement of the problem, you told exactly that this fluid introduction along the porous wall is through a set of orifices perpendicular normal to the streamline's direction, and the way they were withdrawn is also perpendicular to the flow path. And those details are important, so I will show you later on. So with that, calculate a coefficient for each pair of the station. I'll call it I. Divided by the velocity of each of the station. So if I is 0, that is P1 minus P0. And half velocity squared, or velocity squared, and so on and so forth, at each of the station. What is the unit for this quantity? Pressure divided by half rho v squared. Square bracket, what does that mean? Unit of, right? It's dimensionless. So you should only, as the answer, a pure number, a 1, or -2, or whatever. That is dimensionless. If you have other quantity in it, you're missing something. Right? So, 0 to 1, I'm not going to say anything. You have done this problem before, I won't give you any hints. Again, I want the answer to be just a pure number. From 1 to 2, can I use Bernoulli? No. No, you're told turbulent mixing, no streamline. So already you drop Bernoulli. Having said all of that, what is the one equation you can always use, no matter what? Continuity. You need that for every station, and that's, I hope, is obvious. Doesn't matter it's mixing, doesn't matter it's heat added, I don't care. You have to satisfy continuity. Okay? So that's part I want to give you some hints. From 1 to 2, if I look carefully on the diagram, from 1 to 2, excuse me. Where flow was specifically told is being added. Normal, perpendicular to the main flow direction. I will suggest you draw a control volume inside the wall. And I'm going to give you away the problem. You will use momentum equation. Because that's the only thing left that you can hope to relate the pressure difference between 1 and 2. When you draw your control volume inside the wall, there's no anchoring force. It's all internal. There's nothing that will exert an internal anchoring force on the fluid. The real challenge for you is for the momentum in the x direction of the fluid being introduced. How would that affect the momentum equation? When you were told specifically the fluid entered the flow perpendicular. All right, I will leave you to think about it. Okay? The next part is the tricky part. So, this may be in the quiz. Euler's equation, or rather, rephrase myself. Bernoulli equation come from two choices. Energy equation or momentum equation. Pick one. Momentum equation. We spent 2 lectures on Euler's equation just to revisit or reinforce that is the momentum equation. As such, heat addition had no bearing on the problem. And I will stop at that. Okay? Now the last part is also tricky. From 3 to 4, you may be tempted to think, oh, maybe I should use momentum the same way I did from section 1 to 2. But I will ask you when you draw your control volume inside the channel, for a chunk of fluid that go along in the x direction, as it exit my control volume, does it carry any x momentum? You have to think about that one. I'm not going to give you the answer. All right? And contrary to that, or aside from that, can you visualize, can you argue and convince yourself, despite all this suction of the flow or the fluid away from my channel, can I follow a streamline from 3 to 4? Okay, I'm giving away half the problem, because I think it's important. Without that, you will struggle big time. Just to make you feel good, this is a PhD qualifying problem that I took when I was a graduate student at MIT, and I didn't get it. So have fun.
So what I'm hearing is that this is extra credit for the homework?
No. I didn't say that. I just said you should enjoy it with a glass of wine. Okay, so I don't think the quiz take 10 minutes, so let me just touch on something that's a repeat. It's a repeat, okay? This has to do with dimensional analysis and unit. And I am just not telling you anything new. What's the unit of this? You have to think you're in trouble. What's the unit of this? How do you know? Which time you look at? What is this called? It is pressure. They're all pressure. I don't have to say anything. Right? But what is this pressure called? Dynamic. What's the unit of this? Velocity squared. Very good. Velocity squared. Here's the tricky part. What is the physical interpretation of this term? This is not head. The next one is head. What's the unit of the last equation? Length. Head. This is what we call head. And the dynamic pressure now become a dynamic head. And pressure divided by rho g is also a length. Just like you tell me atmospheric pressure is 760 millimeter of what? Mercury. It's a length. You give me a length, I can translate it to pressure. Okay? Next time when we come back, we'll try to interpret what actually physically meant by each of this formulation of Bernoulli. It's very interesting. Some has actually connotation of energy per unit mass, and some has interpretation of energy per unit weight. But with that, I will stop here and give you time to do the quiz. And when you're done, just drop the quiz off the front, and you can leave.